Welcome to Deep Dive with Phil and Emily. Today, we're going to tackle this thing called a feature map matrix.
Oh, yeah. It's
a core concept in machine learning, and we're going to try and break it down so you can really understand how it works.
It's kind of like a secret ingredient that helps algorithms make sense of all that data.
Gotcha.
Like translating data into a language that the algorithms can understand.
Okay, that's a great analogy. So we've got some lecture notes and some code examples to help us out here.
Yeah.
Pre-processing data, what's that all about?
Well, imagine you're baking a cake.
Okay.
And before you even think about mixing the ingredients, you need to prep them, like measuring out the flour, chopping the nuts, softening the butter.
Right.
Pre-processing is similar. It's about getting your data ready for the algorithm to use.
Okay, so what are some ways we prep this data? The notes mentioned turning categories into numbers.
Right.
That sounds kind of weird.
It is essential, though. So let's say you're trying to predict whether people will go to the beach based on the weather forecast: sunny, cloudy, rainy. Those are categories.
Right.
But algorithms love crunching numbers.
Yeah.
So we might assign a number to each weather type. Sunny could be 0, cloudy could be 1, rainy could be 2.
So we're giving the algorithm numerical values to work with instead of words.
Exactly.
Gotcha.
Another key step is making sure that all our data is on a similar scale.
Yeah.
So imagine trying to predict house prices based on square footage and the number of bathrooms.
Right.
So square footage might be in the thousands.
Yeah.
While the number of bathrooms is usually a single-digit number.
Right. Those are totally different scales. Would that mess things up?
It could.
Oh.
The algorithm might mistakenly think that square footage is more important just because it's a larger number.
Okay.
To avoid this,
yeah,
we use techniques like centering and scaling to put everything on an even playing field.
So we're preventing any one feature from dominating the algorithm's attention.
Exactly.
Okay.
And once our data is prepped and ready to go, that's where our star player, the feature map matrix, comes in.
Okay, I'm ready to meet this star player. What does it actually look like?
So imagine you're trying to predict house prices.
Okay.
Based on just one feature, square footage. Let's say your data includes houses with 1,000, 1,200, and 1,550 square feet.
Okay.
Your feature map matrix would be a simple list: 1,000, 1,200, 1,550.
So just a plain list of the square footage for each house?
Almost. There's one tiny but important addition. In most cases, we add a 1 at the beginning of each entry.
Okay.
So our matrix becomes 1, 1,000, 1, 1,200, 1, 1,550. This one helps account for a constant term in our prediction function.
Interesting. So there's more to it than just listing the data points.
Right.
Is that because we might have more features to consider?
You got it. Things get more interesting when we have multiple dimensions. Let's bring back our example with square footage and number of bathrooms.
Right. So now we're dealing with 2 features instead of 1. How does that change our matrix?
Now, instead of a single list, our feature map matrix becomes a table with 2 columns.
Okay.
One for square footage and one for the number of bathrooms. Each row represents a house in our data.
Okay, so if our first house has 1,000 square feet and 2 bathrooms, the first row of our matrix would be 1,002.
Exactly. You're getting the hang of this.
Okay.
Now remember, those functions we talked about, the ones that help us predict house prices based on these features.
Yeah, the ones with the mysterious weights we need to figure out.
That's right. The feature map matrix is how we organize our data to plug it into those functions and solve for those weights. Think of the weights as the knobs and dials we adjust to get the most accurate predictions.
So the feature map matrix sets the stage for finding those magic weights. But how do we actually solve for them? I remember you mentioned a couple of methods: gradient descent and the closed form solution.
We've got a great memory.
Yes.
Let's start with the closed form solution. It's like a shortcut. Using some linear algebra magic, we can directly calculate the best weights in one shot.
No need to take tiny steps, like with gradient descent.
Exactly. With the feature map matrix, we can transpose some matrix multiplication and the actual house prices from our data to get those weights in a single elegant equation.
Sounds pretty efficient.
Yeah.
But is there a catch?
Well, for massive data sets with tons of features, the closed form solution can be computationally expensive.
Oh, okay.
It's like trying to solve a giant Sudoku puzzle.
Right.
It's possible, but it might take forever.
So that's where gradient descent comes in handy.
Precisely. Gradient descent is more like taking a scenic hike.
Okay.
We take small steps in the direction that reduces the error in our predictions.
Right.
The feature map matrix helps guide those steps ensuring we're moving towards the optimal weights.
So it's a slower but potentially more manageable approach for a larger data set.
You got it. Both methods have their pros and cons. The choice depends on factors like the size of your data and the complexity of your model.
Okay, I'm following so far. We've got our prepped data, our feature map matrix guiding the way, and we can choose our weapon,
Right.
gradient descent, or the closed form solution to find those precious weights. What happens next? We finally get to make some predictions.
That's right. Once we have those weights, we can apply them to our function along with new data points, say the square footage and number of bathrooms of a house we haven't seen before.
Okay.
And voila, we get a prediction for its price.
It's amazing how this all comes together. It seems like we've mainly talked about linear relationships between features and our target house prices in this case. But what about situations where things aren't so straightforward? What if there's a curveball in the data?
That's where things get even more interesting. Remember polynomial regression?
Yeah, that sounded a bit more complex.
It is, but it allows us to capture more nuanced relationships in the data. Instead of just using the raw square footage, we might also include its square footage multiplied by itself.
Why would he do that?
Imagine housing prices in a certain area increase more rapidly as the square footage goes up.
Okay.
Squaring the square footage helps our model capture that accelerating trend.
So it's like adding a booster to our prediction power. How does this affect our trusty feature map matrix?
Instead of just 2 columns for square footage and number of bathrooms, we add a third column for the square footage.
Okay.
Each row now has an extra piece of information.
So our feature map matrix is getting more sophisticated, just like our model.
Exactly. We're giving the algorithm more tools to work with, allowing it to learn more complex patterns from the data.
This is all starting to click. But what if we want to consider the combined effect of square footage and bathrooms? Like maybe having more bathrooms adds even more value to a larger house.
Brilliant, Court. That's where interaction terms come into play. We can add another column to our feature map matrix, representing the product of square footage and number of bathrooms. This helps the algorithm understand how these features interact.
Wow, our feature map matrix is becoming quite the powerhouse.
Yeah.
It's amazing how it can adapt to handle these more complex relationships.
It's a versatile tool.
Yeah.
And as you can imagine, things can get even more intricate as we add more features, higher order polynomials, and more interaction terms.
Right.
The feature map matrix keeps everything organized, providing a clear framework for the algorithm to learn from.
This has been such a deep dive.
Yeah.
I feel like I've unlocked a whole new level of understanding about how machine learning works.
I'm thrilled to hear that. Remember, this is just the tip of the iceberg.
Right.
The world of machine learning is vast and constantly evolving, but having a solid grasp of the feature map matrix is a fantastic foundation for exploring further.
I can't wait to see what other mysteries we can unravel.
Yeah.
So we've explored how these feature map matrices work with like linear and polynomial regression.
Right.
But, in the notes here, it also mentions this thing called nonlinear feature maps. Is that related?
It is. Okay. And it might seem a bit counterintuitive, but even when we are dealing with nonlinear relationships in our data, we can still use the power of feature map matrices to help us out.
Okay, my brain's already doing a double take.
Okay.
How can we use linear techniques for nonlinear problems? It's like trying to fit a square peg in a round hole.
It is a bit like that.
Okay.
But the feature map matrix is the magic tool that helps us make that seemingly impossible feat happen. Think of it as a translator, converting our nonlinear data into a form that linear algorithms can understand.
Can you give me an example? I'm having a little trouble picturing how this actually works in practice.
Absolutely. Imagine we're trying to build a model that can distinguish between images of cats and dogs.
Okay.
If we just look at the raw pixel values of the images, it's really hard to draw a straight line to neatly separate cat images from dog images.
Right, that makes sense. Cats and dogs have all sorts of different features, shapes, and sizes. There's no one single line that can like perfectly divide them.
Exactly. But we can use this clever trick called a kernel trick. It's like giving our data a makeover, transforming it into a higher dimensional space where those nonlinear relationships become easier to untangle.
So we're essentially taking our messy, nonlinear data and finding a way to view it in a space where it becomes more linearly separable.
You got it.
Okay.
It's like taking a tangled ball of yarn and carefully winding it into neat separate balls.
Yeah.
And the feature map matrix helps us represent this transformed data in a way that our linear algorithms can work with.
That is blowing my mind a little. So even though the underlying relationship in our data is nonlinear, the feature map matrix helps us create a representation where linear techniques can still be effective.
Precisely.
Wow.
It's a powerful tool that allows us to extend the reach of linear methods to a wider range of problems. And as you delve deeper into machine learning, you'll find that the feature map matrix is a recurring theme showing up in various algorithms and techniques.
Wow. I'm starting to see that the feature map matrix is a real workhorse in machine learning. It's like the unsung hero quietly working behind the scenes to make all these complex algorithms possible.
It really is. And understanding how it works gives you a much deeper appreciation for the elegance and power of machine learning.
This deep dive has been an incredible journey. I feel like I have a much clearer understanding of how data is transformed and used to train machine learning models. Thanks for being such a patient and insightful guide. This has been really fun.
My pleasure. It's been a joy exploring this fascinating topic with you.
Yeah.